In 2023, a spacecraft the size of a small car, traveling 45,000 miles per hour through the darkness between stars, sent back data that stopped a room full of NASA engineers cold. Not the exciting kind of cold, the kind where someone has just handed you a prize. The other kind. The kind where you read a number on a screen and quietly check your math 3 times because the alternative explanation is something none of your training prepared you for. What Voyager 1 detected at the edge of interstellar space has forced scientists to rewrite assumptions that have stood unchallenged for decades. And the explanation they have offered so far? Most physicists are not buying it. Who built Voyager and why it matters? To understand why what Voyager 1 found matters so deeply, you need to understand what Voyager 1 actually is. And I do not mean the technical specifications, though we will get to those. I mean what it represents. Because there is no other object in human history quite like it. In the early 1970s, a group of engineers and scientists at NASA's Jet Propulsion Laboratory in Pasadena, California, realized something extraordinary. The outer planets of our solar system, Jupiter, Saturn, Uranus, and Neptune, were aligning in a configuration that only occurs once every 175 years. A spacecraft launched at exactly the right moment could use each planet's gravity as a slingshot, gaining speed from one encounter and using that momentum to reach the next, essentially getting a free ride across the outer solar system. They called it the Grand Tour. NASA approved the mission in 1972. Voyager 1 launched on September 5, 1977, 16 days after its twin Voyager 2, because the launch windows for their different trajectories made that the more efficient sequence. Yes, Voyager 1 launched second and is still called Voyager 1. Space agencies name things however they want, and nobody can stop them. The spacecraft weighed 722 kilograms and was equipped with instruments designed to measure magnetic fields, charged particles, plasma waves, and cosmic rays. It carried a golden record, literally a phonograph record plated in gold, containing sounds and images selected to represent life on Earth. Greetings in 55 languages. Music from Bach to Chuck Berry. The sound of rain, surf, and a mother's first words to her newborn child. Someone decided that if an alien civilization ever found this spacecraft drifting through interstellar space, they should hear Chuck Berry. That is either the most human thing we have ever done, or a complete disaster depending on how you look at it. Voyager 1 flew past Jupiter in March 1979, sending back images of the Great Red Spot that rewrote atmospheric science. It passed Saturn in November 1980, discovering new moons and revealing the complex structure of Saturn's rings in detail no telescope had ever captured. Then it was done with planets. NASA deliberately aimed it at a trajectory that would carry it up and out of the plane of the solar system, and eventually beyond everything we had ever touched or measured. By 2012, Voyager 1 was more than 11 billion miles from Earth. It had been traveling for 35 years. The engineers who built it were mostly retired or gone. The computers it used were less powerful than the device in your pocket. And yet it was still transmitting. Still sending data back across a distance so vast that the signal, traveling at the speed of light, took over 17 hours to reach Earth. That alone is remarkable. But it is what Voyager 1 was approaching that made it historically significant. And to understand that, you need to understand what lies at the edge of the solar system, and what scientists expected to find there. The edge of the solar system. And what we thought was there. The sun does not just emit light. It constantly releases a stream of charged particles, electrons and protons, moving outward in all directions at speeds of up to 500 miles per second. This is called the solar wind. It is not a metaphor or a poetic description. It is a real physical phenomenon, measurable and relentless, and it extends far beyond the planet. As the solar wind travels outward from the sun, it eventually runs into the material that fills interstellar space, the thin gas and charged particles that drift between star systems. At some point, the solar wind slows down, stops, and the influence of our sun essentially ends. The boundary where the solar wind can no longer push outward against interstellar pressure is called the heliopause. Everything inside the heliopause is technically still part of our solar system. Everything outside it is interstellar space. Scientists had been theorizing about the heliopause for decades before any spacecraft came close to reaching it. The models they developed were based on our understanding of plasma physics, magnetic fields, and the known properties of the solar wind. These were not casual guesses. They were the result of some of the most rigorous scientific modeling ever attempted, built by researchers who had spent entire careers on this one question. And the models produced some confident predictions. The transition into interstellar space would be gradual. The magnetic field direction would shift dramatically as the spacecraft crossed from solar influence to interstellar medium. The density of plasma, ionized gas, would increase measurably outside the heliopause. The energy and behavior of cosmic rays, high-speed particles arriving from outside the solar system, would change in predictable ways as Voyager 1 moved through the boundary region. These predictions were detailed enough and specific enough that scientists felt reasonably certain they would know the moment Voyager 1 crossed the heliopause. They had built the instruments to detect exactly that transition. They had been waiting over 3 decades for it. They were confident. Confidence, as it turns out, is a complicated thing when you are dealing with territory no human instrument has ever entered. Voyager 1 crosses the heliopause. In the summer of 2012, the instruments aboard Voyager 1 began detecting something. The level of cosmic rays arriving from outside the solar system started rising sharply. The intensity of particles associated with the solar wind dropped dramatically. The data was doing exactly what the models predicted it would do at the heliopause crossing. On August 25, 2012, NASA scientists determined that the Voyager 1 had crossed the heliopause and entered interstellar space. It was the first human-made object in history to do so. The announcement was made in September of 2013, after months of careful analysis, because these are scientists and they do not announce things until they are sure, unlike the rest of the internet. The scientific community celebrated, and they had every reason to. This was not just a milestone for NASA. It was a milestone for the species. A machine built by human hands had left the solar system, had crossed the boundary that separates our star's influence from the vast darkness between stars. Whatever you think about government space programs, whatever your opinion on the budget allocations of federal agencies, this was extraordinary. But even as the celebration was happening, something was quietly wrong. One of the predictions had not been met. A very specific prediction about the magnetic field. The models predicted that as Voyager 1 crossed the heliopause, the direction of the magnetic field it was measuring would rotate significantly. Outside the heliosphere, in true interstellar space, the galactic magnetic field should be oriented differently from the solar magnetic field. The crossing should have shown a clear directional shift. It did not. The magnetic field direction barely changed at all. Scientists had an explanation ready. The models were approximate, they said. The boundary region was more complex than anticipated. The measurements would likely show the expected shift over time. There were enough caveats and qualifications that the anomaly was absorbed without too much alarm. That explanation held for several years. And then, 2023 happened. The anomaly. What scientists cannot explain here is where the story gets genuinely strange. And I want to be precise about this because what I am about to describe is not speculation or fringe science. This is documented in peer-reviewed literature and in NASA's own communications about the mission. In late 2022, Voyager 1 began sending back corrupted data. Specifically, the flight data system, the onboard computer responsible for packaging scientific data before transmission, started producing readings that did not make sense. The data appeared to show the spacecraft in random orientations, impossible orientations. positions that contradicted what mission controllers knew about Voyager 1's actual trajectory. One of the data readouts was cycling through a repeating pattern of ones and zeros that corresponded to no instruction or measurement in the spacecraft's entire programming library. Engineers described it as gibberish. 5 months passed. Teams of engineers worked the problem, some of them consulting documentation written 40 years ago by colleagues who were no longer alive, because that is the situation you are in when you are troubleshooting hardware from 1977. In May of 2023, they identified the source. A single chip in the flight data system had failed. It was storing corrupted code and transmitting it as if it were valid data. The fix required reprogramming the spacecraft remotely, sending new instructions across 24 billion kilometers of space at the speed of light, and then waiting 45 hours for confirmation that the commands had arrived and been executed. Let that sit for a moment. 45 hours to find out if your repair worked. The engineers who sent those commands went home, slept, came back, and still had to wait. When the fix was confirmed and clean data began flowing again in late 2023, everyone expected a return to normal. Instead, they got something far more troubling than a broken chip. The data that came back was functioning correctly. It was accurate. It was readable. And it was showing measurements from interstellar space that were, in the precise language of the scientists analyzing them, inconsistent with current models. The plasma density in the region Voyager 1 was traveling through was significantly higher than predicted. Not slightly off. Significantly higher. The kind of discrepancy that does not get explained by rounding errors or instrument calibration drift. The direction and intensity of the magnetic field remained stubbornly different from what models of the local interstellar medium said it should be. Voyager 1 was not in the magnetic environment it was supposed to be in. And then there were the particles. High-energy electrons streaming toward Voyager 1 from a direction that the model said should be largely empty. Not non-existent, but not crowded with accelerated particles either. The particles were arriving in numbers and from angles that suggested some kind of energetic process happening somewhere ahead of the spacecraft in the direction of its travel. Something was accelerating particles in interstellar space, in a region where our models said very little of interest was happening. None of these anomalies individually would constitute a crisis. Science is full of measurements that do not perfectly match models on the first attempt, but all of them together, occurring simultaneously, pointing toward a region of interstellar space that should be relatively quiet and uniform, was a different kind of problem. Scientists use a phrase for this situation. They say the data is telling us something. What they mean, though they are too careful to say it plainly, is that something out there is not what we thought it was. The silence of 2023. The communication situation in 2023 deserves its own chapter because it reveals something important about how fragile our connection to this spacecraft actually is, and how much depends on systems that were designed before most people watching this were born. When Voyager 1 began transmitting corrupted data in late 2022, engineers faced a problem with no modern precedent. The spacecraft's onboard computers operate on approximately 69.6 kilobits of memory. For reference, a single low-resolution digital photograph on your phone takes up more memory than the entire computer system running Earth's most distant spacecraft. The programming language the system uses is essentially extinct. The engineers who wrote the original code are in their 70s and 80s if they are still alive. Documentation for some of the spacecraft's systems exists only in physical paper files stored in archives. This is not a criticism of NASA. It is just the reality of operating hardware that was never meant to last this long. Voyager 1 was designed for a 4-year mission. It has been operating for 47 years. Nobody planned for this. Nobody could have. When the chip failure was identified and the repair strategy was developed, the team had to be extraordinarily careful. You cannot send Voyager 1 to a repair shop. You cannot upgrade its software with a patch download. Every command sent to the spacecraft is a one-way communication across 24 billion kilometers. There's no undo button. If you overwrite the wrong memory location or send a corrupted command, you could permanently silence the most scientifically significant spacecraft in human history. The fact that they fixed it is, without exaggeration, one of the most impressive feats of remote engineering ever accomplished. A team of people, using 40-year-old documentation, reprogrammed a computer 24 billion kilometers away in a region of space no instrument had ever operated in before, and they got it right on the first try. And the data that came back after the fix was what shook them. Because a broken instrument giving you wrong numbers is something you can work with. But a working instrument giving you numbers that should not exist is a different problem entirely. That means the universe is the one behaving unexpectedly, and the universe does not accept bug reports. The theory scientists are proposing. So what is actually happening out there? What do scientists think is causing what Voyager 1 is detecting? The honest answer, and this is the part that tends to get buried in the careful language of scientific papers, is that nobody is certain. There are several competing explanations, and it is worth going through them because each one reveals how much we do not know about the region of space our spacecraft is currently crossing. The first explanation, the one that mainstream researchers lean toward publicly, is that our models of the local interstellar medium are simply incomplete. The interstellar medium is not uniform. It is not a smooth, featureless sea of thin gas and magnetic field lines. It has structures, density variations, boundaries within boundaries. The region of interstellar space that Voyager 1 is crossing may have local characteristics that our models, built from observations made at a distance, did not accurately capture. This is a reasonable explanation. It is probably partly true. But it does not fully account for the scale of the discrepancy in the plasma density readings. The measured density is not slightly higher than predicted. It is more than 40 times higher in some readings. That is not a local variation. That is a fundamentally different environment than the models described. The second explanation involves something called the hydrogen wall. At the outer edge of the heliosphere, solar wind particles pile up against the incoming interstellar medium, creating a denser region of hydrogen. This was predicted theoretically and has been observed indirectly. Some researchers suggest that Voyager 1's trajectory is taking it through regions of this wall that are denser and more energetically active than expected. This is a more interesting explanation, but it has a problem. Voyager 1 crossed the heliopause in 2012. It has been in interstellar space for over a decade. The hydrogen wall is at the heliopause boundary, not deep in interstellar space. If the anomalies were concentrated at the heliopause crossing, the hydrogen wall explanation would be more compelling. But the anomalies have persisted and in some cases intensified as Voyager 1 moves further from the Sun, which is the opposite of what a boundary effect should do. The third explanation is the one that researchers discuss more carefully in the language of possibilities and further study rather than conclusions. The magnetic field readings from Voyager 1 suggest that the local interstellar magnetic field in this specific region of space is oriented differently than the galactic magnetic field models predict. This could mean that Voyager 1 has entered a bubble or filament of interstellar material with its own distinct magnetic history, a region that has been shaped by forces, possibly an ancient supernova shockwave, possibly a different stellar wind, that our models of the broader galactic neighborhood did not account for. This explanation is gaining traction among researchers and was the subject of a significant paper published in 2023. The idea is that our solar system sits inside a region of interstellar space called the local bubble, a vast cavity in the galactic gas carved out by supernova explosions millions of years ago. The boundary of the local bubble may have structure and complexity that our models have not resolved. Voyager 1 may be giving us our first direct measurements of that structure. And then there is the fourth explanation. The one that does not get said out loud in press conferences but does appear in the margins of conversations between researchers after the official presentations end. The possibility that there is some physical process operating in this region of space that current models do not include at all. Not a refinement of existing physics. A gap. Something happening that our theoretical framework does not have a category for yet. Nobody is calling it impossible. They are just not calling it anything yet. What this means for everything we think we know. Step back for a moment and think about what it means if the models are wrong. Not slightly wrong, which models routinely are. Structurally wrong. Wrong about something fundamental about the environment that exists just beyond our solar system's boundary. Every plan for future deep space travel is built on models of interstellar space. The energetic particle environment determines how much radiation shielding a crewed spacecraft would require. The plasma density affects how propulsion systems would perform. The magnetic field structure determines navigation strategies for any spacecraft using electromagnetic systems. If the interstellar medium looks significantly different from what current models predict, then our engineering assumptions for hypothetical interstellar missions are built on uncertain foundations. This matters practically, not just theoretically, because serious proposals for robotic interstellar missions to Alpha Centauri and beyond, are currently being developed and funded. The Breakthrough Starshot Initiative. Various NASA concept studies. All of them use current models of interstellar space to plan their designs. There is also a deeper implication for stellar science. If the local interstellar medium behaves differently than predicted, it raises questions about how we model other star systems and their heliospheres. When astronomers observe distant stars and try to understand the space around them, they use the same theoretical framework that Voyager 1 is now complicating. Every conclusion we have drawn about the environment around other stars is filtered through models that may need revision. And here is the implication that nobody says plainly, but everyone in the field understands. The heliosphere is not just the edge of the solar system. It is our planet's outermost protective shield. The sun's magnetic bubble deflects a significant portion of galactic cosmic rays, high-energy particles from supernovae and other violent stellar events that would otherwise bombard Earth. The structure and strength of that shield depends on the interstellar environment pressing against it from the outside. If that environment is more complex and variable than our models account for, then our understanding of how well protected Earth actually is may also need revision. That is not a statement designed to alarm anyone. Cosmic ray flux has varied throughout Earth's history and life has persisted. But it does mean that the anomalies Voyager 1 is detecting are not abstract academic concerns. They are connected to questions about the long-term habitability of our planet. The golden record problem. There is something else about Voyager 1's current situation that I find genuinely haunting, and I think it is worth pausing on. Not the technical anomaly, something else. Voyager 1 is carrying the golden record, the most deliberate and considered message humanity has ever sent into the cosmos. Carl Sagan and a small committee spent months selecting what to include. The sounds, the music, the images encoded on that gold disc were chosen to represent something true and essential about what life is like on this particular planet orbiting this particular star. That record is now in interstellar space, in territory we do not understand, moving through a region that is behaving in ways our best models cannot explain, carrying greetings in 55 languages into a neighborhood we apparently know far less about than we thought. There is an irony here that I cannot quite shake. We sent our most carefully crafted message to the stars, and the journey has revealed that we understood the destination far less than we believed when we launched it. We wrote a letter to the cosmos, and the cosmos responded by showing us how much we had wrong about the address. Carl Sagan believed, deeply and publicly, that the universe was knowable, that the application of human intelligence and the scientific method would, over time, dissolve mysteries and reveal comprehensible truths. He was right about that in the broadest sense. But he also understood something that sometimes gets lost in the celebration of scientific progress. The universe is under no obligation to be simple. it is under no obligation to match our models. And the distance between what we know and what we think we know can sometimes only be measured by sending a small machine 47 years into the darkness and listening very carefully to what it says when it gets there. Voyager 1 is saying something right now. Every 17 hours, a signal crawls across 24 billion kilometers of space and arrives at the Deep Space Network antennas scattered across Earth, and scientists sit down to read what it says. And what it has been saying, with increasing clarity since 2023, is that something out there does not match the picture. What we owe the darkness. Here is where we land. And I want to be honest about what we know and what we do not, because this story exists in the gap between those two things, and that gap is significant. What we know. Voyager 1 is the most distant human-made object in existence, currently over 24 billion kilometers from Earth, and moving further every second. It has been operating for 47 years, far beyond its designed lifespan, and it is still transmitting. It crossed into interstellar space in 2012, becoming the first human-made object to do so. In 2022 and 2023, it experienced a chip failure that was repaired remotely, and the data recovered afterward revealed anomalies in plasma density, magnetic field orientation, and high-energy particle flux that do not match current models of the local interstellar medium. What we do not know. What is causing those anomalies? Whether they represent a local quirk of the specific region. Voyager 1 is crossing, or a more fundamental problem with our models. Whether the high-energy particles streaming from ahead of the spacecraft indicate an energetic process that our models do not predict. Whether the magnetic field discrepancy reflects an ancient supernova remnant, a structural feature of the local bubble boundary, or something for which we do not yet have a category. And here is the part that makes this genuinely important rather than just technically interesting. Voyager 1 is our only primary data point. We have one spacecraft that has been in interstellar space long enough to detect patterns. 1. Everything we are trying to understand about this region of the universe is filtered through instruments built in the 1970s, mounted on a spacecraft the size of a compact car that communicates at a data rate slower than a 1980s-era dial-up modem. We are trying to understand an ocean with one probe. Voyager 2 is also in interstellar space, having crossed the heliopause in 2018 on a different trajectory. It is providing comparison data, and some of the anomalies Voyager 1 has detected appear in Voyager 2's readings as well, which makes the local quirk explanation less satisfying and the structural model problem explanation more troubling. When two independent spacecraft on different trajectories both show readings that do not match predictions, the anomaly is no longer in the measurement. It is in the model. What Voyager 1 has done, over 47 years of operation and now in the final phase of its transmitting life before its power supply falls below the threshold needed to run scientific instruments, is reveal the limits of our knowledge in the most vivid and concrete way possible. We can build equations that describe the interstellar medium. We can run simulations on supercomputers. We can make observations from Earth using radio telescopes sensitive enough to detect signals from the edge of the observable universe. And we can still be wrong about what it actually looks like 24 billion kilometers away. The anomaly Voyager 1 found is not the end of the story. It is a door. On one side of the door is everything we thought we knew about the space between stars. On the other side is whatever is actually there. And for the first time in human history, we have an instrument on the other side sending back reports. The reports are saying the room looks different than we expected. What we do with that information, how seriously we take it, how aggressively we pursue the question, how willing we are to let evidence complicate comfortable models. That is not a question about Voyager 1. That is a question about us, because the universe just handed us a data point it took 47 years to collect. And the data is telling us something. We owe it to the engineers who built Voyager 1, and to the scientists who have spent careers reading its signals, and honestly to ourselves, to listen carefully. Something is out there at the edge of interstellar space. It is not what we thought. And we are barely beginning to understand the question, let alone the answer. That is not terrifying. That is the whole point of science. That is what makes it worth doing. Even if, just occasionally, at 17 hours per signal across 24 billion kilometers of empty dark. The universe feels very large, and our models feel very small.